Hello friends, welcome to our channel, Gajpal A Learning. In this video we are going to study about the topics: precipitation titration, solubility product, importance of solubility product, calculation of solubility product, factor affecting solubility of precipitate. So let's start. First, precipitation titration. Precipitation titration is a common analytical chemistry technique used to determine the concentration of an analyte in a solution by adding a titrant solution that reacts with the analyte to form a precipitate. This type of titration is particularly useful when the analyte is not easily amenable to other titration methods, such as acid-base or redox titrations. Precipitation titrations are often employed to determine the concentration of various ions, including halides, sulfates, and many other ionic compounds. The key principles of precipitation titration include: first, formation of precipitate. The analyte and titrant react to form an insoluble precipitate. This precipitation reaction typically involves the combination of two ions in the solution to form a sparingly soluble compound. The balanced chemical equation for the reaction is known, and it is important that the reaction goes to completion. Second, stoichiometry. The stoichiometry of the reaction is well defined, allowing for the determination of the exact amount of titrant required to react completely with the analyte. This information is crucial for calculating the analyte's concentration. Third, endpoint detection. The endpoint of the titration is typically detected using a suitable indicator or by monitoring a change in the physical properties of the solution, such as turbidity or color. Common indicators for precipitation titrations include chromates, dichromates, and various organic dyes. Fourth, calculation. The concentration of the analyte is calculated based on the volume of titrant required to reach the endpoint and the stoichiometry of the reaction. The concentration is usually expressed in moles per liter, molarity or m. Next is solubility product. Solubility product, often denoted as KSP, is a fundamental concept in chemistry that relates to the equilibrium constant for the dissolution of a sparingly soluble compound in a solution. It describes the extent to which a solid compound can dissolve in water or another solvent at a specific temperature. The solubility product expression for a generic sparingly soluble compound, such as a salt, AX, is given by KSP equals A plus power N X power M, where A plus and X represent the equilibrium concentrations of the ions A plus and X in the solution, respectively. N and M are the coefficients from the balanced chemical equation for the dissolution of the compound. The value of KSP is temperature dependent and is a measure of the compound's solubility. If the ion concentrations in the solution exceed the KSP value, then a precipitate will form, indicating that the solution is supersaturated. Conversely, if the ion concentrations are below the KSP value, the solution is unsaturated, and no precipitate will form. Precipitation titration and solubility product are interconnected because precipitation titrations rely on the principles of solubility product to determine the analyte's concentration. By carefully controlling the addition of titrant and monitoring the formation of a precipitate, one can use the stoichiometry of the reaction and the KSP value to calculate the analyte's concentration accurately. Importance of solubility product. The solubility product, KSP, is an essential concept in chemistry with several practical and theoretical implications. Its importance lies in various areas of chemistry and science. First, predicting precipitation reactions. KSP values provide crucial information about the solubility of ionic compounds. If you know the KSP value for a compound, you can predict whether it will precipitate when the concentrations of its constituent ions in a solution exceed the KSP value. This is valuable in understanding and controlling chemical reactions and processes. Second, quality control and analytical chemistry. In analytical chemistry, KSP values are used to develop precipitation titration methods for determining the concentration of specific ions or compounds in a sample. This is especially important in industries like pharmaceuticals, environmental monitoring, and food testing, where accurate concentration measurements are critical. Third, environmental chemistry. Understanding the solubility of various substances in natural water bodies is essential in environmental chemistry. It helps predict the fate and transport of pollutants, such as heavy metals and mineral salts, in aquatic systems. Knowledge of KSP values can assist in evaluating water quality and designing remediation strategies. Fourth, Pharmaceutical formulations. In the pharmaceutical industry, the solubility of active pharmaceutical ingredients, APIs, is a critical factor in drug formulation. KSP values are used to predict the solubility of APIs in different solvents, aiding in the development of drug delivery systems and ensuring the bioavailability of medications. Fifth, material science and engineering. In material science, KSP values are relevant for understanding the dissolution behavior of materials, such as ceramics and minerals. Engineers and material scientists use this information to design materials with specific properties and to assess the durability of materials exposed to various environmental conditions. Sixth, geological processes. KSP values play a significant role in geology by helping researchers understand the formation and dissolution of minerals in geological processes. This knowledge is crucial for studying geological formations, mineral resources, and the geochemical evolution of Earth's crust. Seventh, chemical equilibrium. The concept of KSP is a fundamental part of chemical equilibrium. It highlights the relationship between the concentrations of reactants and products in a saturated solution. This understanding is fundamental to many aspects of chemistry, including equilibrium thermodynamics. Eighth, fundamental chemistry education. The concept of solubility product is often introduced in introductory chemistry courses. It helps students grasp fundamental principles of chemical equilibrium and precipitation reactions, laying the foundation for more advanced studies in chemistry. In summary, the solubility product is a critical concept that is widely applied in chemistry, environmental science, materials science, and various industries. It allows scientists and researchers to predict, control, and understand the behavior of substances in solution, making it an essential tool in both theoretical and practical aspects of the chemical sciences. Calculation of solubility product. The solubility product, KSP, of an ionic compound can be calculated when you know the concentrations of its constituent ions in a saturated solution. To calculate KSP, you need to follow these steps. First, write the balanced chemical equation for the dissolution of the compound. Second, identify the stoichiometry of the reaction, which tells you the ratio of ions in the balanced equation. For a generic ionic compound AX, the balanced equation might look like this. AX S equilibrium sign A plus X. Third, determine the equilibrium concentrations of the ions A plus and X in the saturated solution. These concentrations can be obtained from experimental data or calculated based on the amount of the compound that dissolves. Fourth, write the solubility product expression based on the balanced equation. For the generic compound AX, the expression would be KSP equals A plus X. Fifth, substitute the equilibrium concentrations of the ions into the KSP expression. Sixth, calculate the KSP value. Here's a step-by-step example to illustrate the calculation of KSP. Example, calculate the solubility product, KSP, for silver chloride, AgCl, if you know that the concentrations of Ag plus and Cl, ions in a saturated solution are 1.0 x 10 raised to the power minus 5 molar each. The balanced equation for the dissolution of AgCl is AgCl equilibrium sign Ag plus Cl. Solution. First, write the balanced chemical equation. AgCl S rightwards harpoon over leftwards harpoon Ag plus Aq plus Cl Aq. Second, identify the stoichiometry of the reaction. The ratio of Ag plus to Cl ions, that is 1:1. Third, determine the equilibrium concentrations of Ag plus and Cl ions, which are both 1.0 x 10 to the power 5 molar in this case. Fourth, write the solubility product expression. KSP equals Ag plus Cl. Fifth, substitute the equilibrium concentrations into the KSP expression. KSP equals 1.0 x 10 to the power minus 5 m, 1.0 x 10 to the power minus 5 m. Sixth, calculate the KSP value. KSP equals 1.0 x 10 to the power minus 5 by 1.0 x 10 to the power minus 5. To give 1.0 x 10 to the power minus 10. So, the solubility product KSP for silver chloride AgCl is 1.0 x 10 to the power minus 10 at the given conditions. This means that at equilibrium, the product of the concentrations of Ag and Cl ions in a saturated solution of AgCl is equal to 1.0 x 10 to the power minus 5, and no more AgCl can dissolve without violating this equilibrium. Factor affecting solubility of precipitate. The solubility of a precipitate, which is the maximum amount of a solute, typically an ionic compound, that can dissolve in a given solvent under specific conditions, can be influenced by several factors. These factors include: first, nature of the solute in solvent. Under this, a. Ionic strength. Compounds with higher charges tend to be less soluble because they experience stronger ion-ion interactions. b. Ionic size. Smaller ions often have greater solubility because they can more easily fit between solvent molecules. c. Polarity. Polar solvents tend to dissolve polar solutes better, while nonpolar solutes dissolve better in nonpolar solvents. d. Temperature. In general, most solutes become more soluble as temperature increases. However, this is not true for all substances, especially for some salts that exhibit reverse solubility behavior at higher temperatures. Second, pressure. For gases, Henry's law describes how the solubility of gases in liquids increases with increasing pressure. This is why carbon dioxide, CO2, becomes more soluble in soda under high pressure. Third, common ion effect. The presence of a common ion, an ion shared with the solute, can decrease the solubility of a compound due to Le Chatelier's principle. It shifts the equilibrium toward the formation of the precipitate. Fourth, pH of the solution. The pH of the solution can affect the solubility of substances with acidic or basic properties. For example, many metal hydroxides are more soluble in acidic solutions and less soluble in alkaline solutions. Fifth, complex formation. Some ions can form complex ions with ligands in solution, increasing their solubility. This is often seen with transition metal ions. Sixth, agitation and surface area. Increasing the surface area of the solid, example, by grinding it into a fine powder, and stirring the solution can enhance solubility by exposing more solid particles to the solvent. Seventh, temperature. For non-gaseous solutes, as mentioned earlier, in most cases, the solubility of solid solutes in liquid solvents increases with temperature. However, this isn't universally true and may vary for different compounds. Eighth, pressure. For non-gaseous solutes, pressure generally has a minimal effect on the solubility of solids in liquids compared to its effect on gas solubility. However, there are some exceptions, such as the dissolution of gases into certain solvents under high pressure. Ninth, co-solvents. Mixing two or more solvents can sometimes enhance the solubility of a solute that is poorly soluble in a single solvent. The choice of co-solvent depends on the specific solute and solvent system. 10th, complexation. The formation of complex compounds or inclusion compounds can increase the solubility of certain substances in a solvent. It's important to note that the solubility of a substance is a thermodynamic property, meaning it depends on the conditions, temperature, pressure, pH, etc., and the intermolecular forces between the solute and solvent. These factors can be used to control and manipulate the solubility of a substance for various applications in chemistry and industry. Thanks for watching this video. If this video was helpful, TT Hen, please kindly subscribe to our channel. Thank you.